Hi, welcome to AB Video 6.2a Part 2, more on growth and decay. Okay, in the textbook 11 through 14, write and solve the differential equation that models the variable statement. I'm just trying to get you to translate here. So the rate of change of y with respect to x, that should tell you dy dx, varies jointly as, which is equal k times, and it varies jointly as x and L minus y. Okay, note L is a constant and assume that L is bigger than y, which means that L minus y is positive. So what we have is we have this differential equation. I'll bring the y's to the left, the x's to the right, integrate both sides. I get 1 over ln minus y dy. Picture, remember, L is a constant. Picture letting u equal that constant minus y. The derivative would be negative 1 dy, so you would have to introduce and counteract with that negative. And now you're integrating 1 over u du, which is ln u. Now, the reason I don't need the absolute values is we're assuming that L is bigger than y, so L minus y is positive. Integrate the right side, kx squared over 2 plus c1. And therefore now writing it in exponential form, L minus y equals e to the power of that expression. Break that up, e to the negative c1 times e to the negative kx squared over 2, and e to the negative c1 is just another constant c. So another expression, write and solve the differential equation that models the variable statement. Evaluate the solution at the specified value of the independent variable. So here's what they tell us. The rate of change of n is proportional to n. So that's our exponential growth. The rate of change of a quantity is proportional to the quantity. When t equals 0, n equals 250, they're giving you the initial amount. Unfortunately, they're not calling it y, they're calling it n. And when t equals 1, n is 400. That's an initial condition. What is the value of n when t is 4? So obviously I need an equation in n and t. So I translate the rate of change of n, which is dn dt, and if you don't know with respect to what, it'll be with respect to time, plus you can see the t right here, and is proportional to n, which equals k times n. We know that that becomes n equals n0 times e to the kt. They're telling us that n0 is 250. And then so now I have n equals 250 times e to the kt. Now e we know is 2.71 dot dot dot. N and t is what we want. It's the k that we need the value of. And that's why they're giving you the initial condition that when t equals 1, n equals 400, that'll allow us to find k. So you have 400 equals 250 times e to the k times 1, which makes 400 or 250 equals e to the k. Now the book is actually going to solve for k. They're going to just take this equation and get this ugly decimal. Personally, I'm not, and nor will the AP. I'm going to take my n equals 250 e to the kt, and I will replace e to the kt by e to the k to the t. Now I can take e to the k is 400 over 250 to the t, and that'll be your answer, 250 times 400 over 250 to the fourth. In the worksheet, number 2, so going back to number 2, so bacteria grown in a certain culture increase at a rate proportional to the number present. So as soon as you read that, that's dy dt equals ky, which means we know it becomes y equals y0 times e to the kt. It says there are 1,000 bacteria present now, so that'll be the initial amount, y0, and the number will double in 30 minutes. Okay, so there's 1,000 now. In 30 minutes, so replacing t by 30 minutes, there will be double what there is now, which is 2,000. So I can divide both sides by 1,000, and I will end up with e to the 30k equals 2. You can do it with the ti, but I'm going to do it not with the ti. Okay, so I'm going to do this version here. I'm going to go, okay, so this is y equals 1,000 e to the kt. I'm purposely going to replace e to the kt by e to the 30k to the power of t over 30. You can see the 30s would cancel, and this would give you k times t. E to the 30k is 2, and now beautiful equation in y and t. Now they are asking some questions. if y bacteria will be present, t express y as a function of t, which we just did. Then they ask you to estimate on your calculator, but let's confirm. So how many bacteria are present in 2 hours? Well, now that our equation is in y and t, how many are there in 2 hours means I'm going to have to replace t not by 2, but by 120 because they told us that it was 30 minutes. So be careful if they switch up the units of measure. So we have y equals 1,000 times 2 to the power of 120 over 30, blah, blah, blah. And this you don't even need a calculator for this. 2 to the 4th is 16. So here they give you the t and ask you for the y. In the next one, they're going to give you the y and ask you for the t. Oh, no, maybe not. Yes. Uh, find this. Find when will there be 50,000 bacteria present. So now what you're doing is maybe on the next page. Yeah. So when are there 50,000 bacteria present? So you're going to take your equation, you're going to replace the y by 50,000, and we're trying to find the when, which is the t. Divide each side by 1,000, you get 2 to the whatever, and then you could solve either this equation or this equation on your calculator. If you were doing it by hand, you'd still need a calculator at some point to replace this expression. Worksheet number 10. If the half-life of radium is 1,690 years, what percent of the amount present will now be remaining after 100 years, after 1,000 years? Okay, so we know that radioactive decay is, which they don't tell you, okay, radioactive materials decay at a rate proportional to the amount. So it is exponential decay. We know that becomes y equals y0 times e to the kt. So we're going to plug in what they told us, which is after 1,690 years, there'll be half as much left as we started with. So if we start with y0, there'll be half of y0 left. And that'll become 1/2 equals e to the 1690k. Again, I'm going to use my little neat method. So I'm going to rewrite this expression. I'm going to replace e to the kt by e to the 1690k to the power of t over 1690. You can see that the 1690s would cancel and you'd be left with kt. I know that e to the 1690k is exactly 1/2, so I plug that in. And now here's my equation. Now you would think, oh, but I don't have y0. But notice the question doesn't ask you for an amount. It asks you for a percent because they never gave us an initial amount. So it's kind of all we can deal with. So this is our best we can come up with. Usually it's just y and t, but we're stuck with y0. So if you look at question A, it says, what percent of the amount present now will be remaining after 100 years? So all you do is replace your t by 100, and you'll find out that y equals y0 times 0.96. In other words, the amount that will be there is 96% of the original amount. And then the other one is replace t by 1,000, and you'll find out what that equals.